SwayamPrabha. Digital India. Educated India.
So, weird condition, one is the passivity condition, already unusual, yeah, and then there is the zero state observability condition, which is not too unusual. Let me see if I can try to sort of justify this. Let me see, I am not sure if I can. Let us go to the sort of linear system case, yeah, and also we will test this condition in example. So, you will anyway figure it out how to use it. Yeah, it is almost like this LaSalle invariance condition. Yeah, it looks like that. If you see, you have a set which is some function equal to 0, and you are saying it does not contain anything but the trivial solution, that is the 0 solution. Okay. And what is it a solution of? It is a solution of this system, the uncontrolled dynamics. So, this whenever you put the control to 0, you are saying it is the uncontrolled dynamics. Okay, no solution of this uncontrolled dynamics is here except the equilibrium, the 0 solution. Equilibrium itself is a solution, it is a trajectory, well not this but this, but still a trajectory. Okay, is that clear? Okay, great. Now let me try to sort of at least make sense of it and try to connect it with our linear system idea. Yeah, this is our uncontrolled linear system, LTI system, and our output, typical, right. Of course, we assume things like x in Rn, y in Rp and all that, same deal. Typically p will be less than n, yeah, less measurements than states, yeah. Great. Now let us see, how do you write the solution in this case? It is xt is e to the power at x0, correct, just the using the exponential. So, this will give me the output is c e to the power at x0, right. So, how do we, why do we have the observability matrix condition? Because if I expand this, yeah, what is it? Identity plus at plus a squared by 2 factorial t squared and so on, multiplying x0, right. And of course, you can already start to see, I can write this, actually I can write this as an infinite series if you want. This is c ca squared multiplied by something here, yes, yeah, and what you have here is the controllability matrix, sorry, observability matrix, yeah. It does not have to be infinite length, because of I can make the infinite length into finite length. Why? This guy do not need to check this infinite matrix and only need to check the finite matrix. Why? Just 2 words, name of a person, a theorem. Why? Why? Can I shrink this infinite, because this is infinite, right? I hope you believe that this is an infinite series, so obviously it is an infinite length matrix, but your typical controllability, typical observability matrix is only till what? Ca squared until Can minus 1, okay, why? Yeah, just due to Cayley-Hamilton theorem, yeah, because all the higher powers are anyway, you can write them as smaller powers. So, no need to write all the powers, okay. So, this is the observability condition, alright, great. Now, why this? So, let us see what is the set, this set in this case, okay. What is the set in this case? It is in the linear case I am saying that x in Rn Hx is equal to Cx is equal to 0. Okay. So, if I use my solution, this is actually equal to the set of x0 in Rn such that let us see Ca n minus 1 okay, because everything else is now independent of states, right. All this quantity, this is all independent of states. It contains what? It contains time and this matrix, right, because once I use Cayley-Hamilton, I will just have some complicated functions of time here. Is that fine? Just complicate. By the way, each of these will be infinite series inside this, but we do not care about all that. The idea is this. In fact, I do not think this is writable like this. We have to write it in a different way. This is because this is not compatible operation anymore. X0 is in Rn, and this is the what is the dimension of the Gramian? Sorry, the controllability observability matrix. Number of rows is क्या है बताओ? Number of rows is p. Number of columns is n. It's a p cross n matrix. It's a p cross n matrix, right? So I think we'll have to write this not like this. I apologize. I'm going to erase this for those who copied already. This is just doing vector math. I'm not doing anything magical. This is x0 transpose c ca n minus 1 transpose times this vector equal to 0. Yeah, you will get something like this. Okay, you will get something like this. Why I just did, if you notice, this is now compatible, right? Compatibility issue is resolved. Why? This is a 1 by n, right? This is n by p, right? And this is whatever dimension. This is of course appropriate to make it a scalar, right? Okay. So, this is fine. This is now compatible, and you can see that this is now, this is the set. Now, tell me something, what is the set of x zeros that will make this 0? By the way, this is to be for all t and all. T cannot play a spoil sport here, right, because no when I say that the set is 0, it has to be 0. T, there can be no t and all happening there, right? It has to be for all t. T cannot mess it up. So, I am looking at set of all initial conditions, right, such that this product is 0. How did we get this product? Just from here, plugging in the solution for x. Okay, just from here we get this, just plugging in the solution for x, nothing magical, and expanding the exponential and rewriting it in an appropriate matrix product form. That is it. I mean, if you, even if you are not convinced about this, you can go back and think about it. That is not a problem. This is, it will come out to be like this. Now, tell me something. When will this be 0? For what x zeros will this be 0? Anybody? Yes, good call. For x0 equal to 0, yes. Can you give me a slightly more complicated, difficult answer? Like, is that the only choice of x0 for which this will be 0? See, because this can do nothing, right? Like, you can pretty much forget about this, because this is all a function of time, and all this 0 thing has to hold for all time. So, obviously, this product has to become 0. This product has to become 0. When will this product become 0? Yeah, somebody was saying something. Whoever said that word? Null space. Null space, whenever x0 is in the null space of this matrix. What is the null space of this matrix called? I think you guys have either not done this linear system very well or you've forgotten. Unobservable subspace. Unobservable subspace. The null space of this matrix is called the unobservable subspace. Sab bhul gaye. All right. Okay. No problem. Okay. And this is called the unobservable subspace. Okay. So whenever x0 belongs to the kernel of the observability matrix, or the basically x0 belongs to the unobservable subspace, only for those x0 this is 0. Okay. Okay. All right. And once you can find any one x0 like that, you have created a trajectory, right? Because yeah, you understand, right? As soon as I give an initial condition, I have solved this, I obtained a trajectory, right? So for every x0 in the unobservable subspace, I get one such trajectory, right? Now if you say there is nothing but the trivial solution, what are you saying then? You are saying that there is no x0 in the null space other than 0 itself. Okay, so null space is empty is how we say it. Yeah, 0 we don't count. Yeah, so we are saying the null space of the observability matrix is empty, which means system is observable. Okay, system is so what we have just codified in this slightly more complicated language is just the fact that system is observable. Okay, what we are calling this 0 state observability is actually the observability condition that you have for linear systems. At least for linear systems it boils down to that. For nonlinear systems you can have slightly more complicated notions of everything, yeah, which is why it's called 0 state observable. Yeah, so basically you are saying that if you write this condition out for linear time invariant systems, all you are saying is that the system is observable. That's it. Okay, all right, makes sense? No confusion? All right. This? Okay, okay. Your question is why do we say that the system is unobservable? Okay, why do we say that? I defined observability as being able to identify the initial conditions from the outputs. Okay, that was the idea. Now if you look at this expression, yeah, or I mean, or basically this guy is just this guy. If you look at this expression, the question is, can I reconstruct x0 from y? That is the question I am asking. Okay. Now if the system is observable, let us look at the good case. System is observable means this is maximal rank. Observability means its maximal rank, that is only then the kernel will be 0, right. So what is the maximal rank? P, right, because it's an P by N matrix. Wait a second, did I get this correct? This is the P by N matrix or not? C is P by N, C is P by N, this is also P by N. This is not a P by N matrix, ridiculous, I was wrong, you guys did not correct me. This is a, this matrix is a what? P by N times P matrix. Is that correct or not? See, this C itself is a P by N matrix, right? So this is also a P by N matrix, right? Wait a second, wait a second, wait a second. C is P by N. First of all, this is all messed up. Anyway, that's fine. It's supposed to be written in that way. C is P by N, this guy is also P by N, everything is P by N. And how many such entries do I have? But this seems wrong to me. It's very wrong. Yeah, actually this is not the observability matrix itself, this transpose is the observability matrix. This is the observability matrix itself actually. So it's C, CA, that is why it's all coming out to be messy in my head. Yeah, because actually I am sorry, it's just vector arranging the vector and matrix multiplication, nothing magical. This product, like I said, can be written as this guy, and this is the observability matrix, the transpose with the transpose. So now the dimensions are okay. What is the dimension of this? It's what? P by n, np cross n, right? Np cross n, thank God, it's becoming np cross n. Did I get this right? Abhi gadbad lag raha hai. Np cross n, then so this product is not compatible. I didn't get this right then. It is some function of t times c ca can minus 1 times x0 equal to 0. Okay, this is now correct, yeah, because this was an np cross n matrix. The observability matrix is an np cross n matrix, and the x0 is an n by 1 vector. This is now correct. Okay, all right, big mess. But the basic point is, this expression here can be written as this. Okay, now if this can be written as this, yeah, and we are saying that this guy is full rank or maximal rank. What is the maximum rank of this guy? Huh? N. Yeah, because p is of course greater than or equal to 1. So it's n. So it will be an n ranked matrix. Okay, which means what? Which means what? So basically you have some n ranked matrix multiplying x0. It's a solvable system of linear equations. Huh? It's a solvable system of linear equations. Okay, the simple, if you want to think more simply, assume p is 1, single output. It's a single output system. Okay, if it's a single output system, then this is an n by n matrix. So basically what you have is a n by n matrix multiplying x0, which means it's an invertible matrix, right? So I can invert it and get my initial condition. Okay, so that's the whole idea. I need to be able to compute the initial condition from the given data. What is the data? Data is the measurements, that is observability. Therefore, if you have anything in the unobservable subspace, yeah, so these are all funny, it's a funny thing. See, just think about this. Okay, if I have multiple points in the unobservable subspace, x01 and x02, okay, for both of them this is equal to 0, correct? For both initial conditions my measurement was 0. For both initial conditions my measurements along the trajectory are 0. So I cannot distinguish the two initial conditions anymore. Okay, which is why this condition, there can be no trajectory but the trivial trajectory in this set. Okay, so anyway, this is itself a very nice subtle topic. It's not that easy to follow, which is why, and also I am not teaching this, it's more haphazard. So I was just trying to make a comparison. Yeah, in linear systems the idea of observable, unobservable, controllable, uncontrollable, this in itself is a relatively involved topic. I mean, you have to sort of wrap your head around it, takes a little bit of time. Okay, but the idea is, if you have unobservable subspaces, then you will have initial conditions which are indistinguishable by measurements. You can take, measurements and you will not be able to distinguish, okay, between the two initial conditions. Okay, so I mean, you can even say simply something like, let me see, if you have y equal to CEAT x01 and also equal to CEAT x02, if these are the same, because this is the measurement, right, and two different initial conditions, I have the same measurements, then basically these two are indistinguishable. Okay, and if these are indistinguishable, what did I just prove? that CEAT, notice x01 and x02 are different. I just proved that x01 minus x02 is in the null space, and x01 minus x02 is non-zero, not a trivial vector. So, it is in the null space of this, which means observability matrix is not maximal rank. So, you can go both ways, yeah, and sort of understand that you observability, that is being able to construct initial conditions from measurements, requires that observability Gramian or observability matrix be maximal rank, okay, and that condition is what for nonlinear systems is codified in this sort of zero state observable idea. Yeah, again, why it has this funny name is because observability has multiple, there are multiple observability and controllability notions in nonlinear systems, okay, so more complicated, okay, so that's the only reason why we have these multiple notions. Any questions? So, two important definitions: passivity, this we have not sort of connected to linear systems, we might later on, as of now no need to connect it, it is just a general notion or a general property of systems, and the zero state observability, which we have connected to observability of linear systems, alright. Okay.